Hello everyone, I welcome you all to the course UAV design, and today we are going to discuss about wing design technique. The selection and optimization of a wing parameter is a fundamental aspect of an aircraft design. These parameters directly affect the aerodynamic performance, stability, control and structural integrity of the aircraft. Early decisions on wing geometry also influence other subsystems including fuselage integration, landing gear configuration, and control surfaces. Wing vertical location refers to the position of the wing relative to the fuselage center line. It plays a critical role in lateral stability, ground clearance, tail and landing gear design, maintenance, and payload access. There are 4 standard configurations. High wing, mostly this high wing configuration, we'll be using it for logistics aircrafts. For example, C-130, Scan Eagle, which are more stable and good for launcher based unmanned air vehicles. Second one is mid-wing configuration. The example for this configuration is military jets. They are placed at mid-wing only because of their agile in nature. Placing the wing at the mid allows the aircraft to ensure it can undergo maneuvers randomly because it will have clean aerodynamics and it will be structurally complex. Low wing configuration, for example, we have Predator, Global Hawk are the 2 aircrafts which will have a low wing configuration. Generally in aircraft, we have 3 wing configurations, that is high wing, mid wing and low wing. In aircraft application, high wing structures are generally given for a larger aircraft which carries huge payload like C-130. It's completely logistics. It will carry logistics from one point to another point. It will depart from one point and it will reach its destination after completing its range and it will land there. Similarly, we have mid-wing aircrafts. These mid-wing aircrafts are agile in nature and it has a good maneuverable capabilities. The third category is low wing. In this low wing category, in most of the aircraft, it's become ease for the maintenance of these engines. Ground servicemen can easily do the servicing of these engines which are onboarded or podded on this low wing configuration. The next category is parasol wing. Example for this aircraft is vintage light unmanned air vehicles. It's highly visibility downward and less common now. Advantages and disadvantages of wing vertical location. Advantages of having wing vertical location is it increases the lateral stability of high wing. It has better ground clearance. Like if this is the aircraft, this is the engines which is spotted on the high wing. Under the high wing, it has huge ground clearance. Right? So it becomes much more easier. And we have smoother, lower fuselage. Disadvantages of having a high wing structure is long landing gear. This landing gear will be very long and it will have very heavier retraction mechanism. Advantages of having low wing configuration. Advantages of having this low wing configuration is it will have shorter landing gear and it will be efficient in integration of the fuel tanks, because it will be at the lower. Directly from here, the fuel from this wing, uh, because of the gravitational force, it will pass directly to the engine. It will pass like this and becomes easy from here, from the under the fuselage. And the disadvantage in this low wing configuration is it's prone to ground effect during takeoff and landing, and it will have low lateral stability. A tip for all unmanned air vehicle designers is, for the UAV which requires launcher takeoff or operate from rugged terrain, high wing is preferred, ensuring whenever it is taking off, whenever it takes off, it doesn't collide and it doesn't damage the wing structure. The wing incidence angle is the angle between the fuselage reference line and the wing root chord line. If we see from the side view, if we observe from the side view, the wing incidence angle is the angle between fuselage reference line, right? This is the FRL, right, which passes through the center of the aircraft, which equally divides the aircraft vertically in two halves, upper half and lower half, right? And this IW is the angle between this fuselage reference line and wing root chord line. So this is the root of the wing. Right? In three-dimensional view, it will look like this. So this is root, wing root, and this is wingtip. And the chord line is the line which joins, the straight line which joins from the leading edge to trailing edge. So the angle between this line and this FRL is your incidence angle. Let's take another aircraft example here. Instead of taking a mid-wing configuration, we'll take high-wing configuration here. Okay, and this is the fuselage reference line for high-wing. Okay, and this is the chord line. And now this angle is IW, incidence angle. In this case, this was mid-wing configuration. Therefore, it was very difficult to trace it out what is incidence angle. Here we can see in the high wing configuration, and even for the low wing, if we take an example of low wing, it will be somewhere here, and this will be, so the angle between these two is incidence wing angle. It is also referred as wing setting angle, which is denoted by alpha set. The fuselage center line lines in the plane of symmetry and is usually defined parallel to cabin floor. The wing must be able to generate the desired lift coefficient during cruising flight. Cruising flight is lift equals to weight, thrust equals to drag. This phase is cruising phase. This is takeoff, climb, cruise, descent, land. The design requirement naturally matches with the wing aerofoil angle of attack corresponding to airfoil ideal lift coefficient. As soon as the wing ideal lift coefficient is determined, a reference to CL alpha graph is demonstrated, which with the wing setting angle. The typical number of wing incidence for a majority of aircraft is between 1 to 4 degrees. This is CL versus alpha curve. This is lowercase l, so it is giving for airfoil, and if I write as C suffix L, then this is for the wing, because it's a 3D component. This is lowercase l is representing airfoil. So for symmetric airfoil, this becomes CLmax and this becomes alpha stall. From here, the lift tends to fall down. So this is alpha stall. From here, the lift starts to lower. Same thing with the wing. This is it's a symmetric airfoil. So assume it is NACA 0012. So with the same airfoil, if we have a wing configuration, it will have same alpha stall, and this is CLmax. This is the slope, which is A0, which is dCl by d alpha, and for wing it will be dCl by d alpha. Next, the very important term in wing design is aspect ratio. Aspect ratio is defined as the ratio between wingspan and the wing aerodynamic chord. AR equals to B upon C. This B is wingspan and this C is chord length. The wing planform area for a rectangular or straight tapered shape is defined as the span times the mean aerodynamic chord, which is S equals to B into C. B is wingspan, C is chord length. This is a schematic diagram of a trapezoidal wing where we can see aerodynamic center in a straight wing. This is the aerodynamic center AC. This is the sweep angle. This is the sweep angle at the leading edge. This is mean aerodynamic chord. It is the shortest distance joining leading edge to trailing edge. This is tip chord. This is root chord. From here to here is root chord. This is tip chord. As it is plane in the plane of symmetry, same thing will be here. Whatever the length is here, the same length we'll have here, and this will be common for both. Right. This is the aerodynamic center aligned. Typical values of unmanned air vehicles are aspect ratio values 6 to 25. For gliders, it will have high aspect ratio, or approximately it is 30, and fighter jets, it will be lower, approximately between 4 to 6. If an aircraft has low aspect ratio, it will have agile nature such that it can undergo various maneuvering randomly. If the aspect ratio is higher, it becomes quite tough for an aircraft to undergo maneuvers. So most of the commercial aircrafts are having high aspect ratios. Therefore, they perform only pitch up, pitch down, banking, and slight roll. That too banking. They'll just roll, tending that it's banking. It's not completely roll. It's just bank. It will just change like this in order to just change the direction. It doesn't roll completely, but yes, there are control surfaces which can actually ensure that it can roll. But yes, because passengers sitting inside, to ensure that a smoother flight, it will just bank on the left and right for just changing the direction of the flight, and the other aspect is yawing. Whereas a fighter aircraft, it can climb, it can dive, it can again go up, vertical climb, it can again dive, nose dive, can go for spiral climb, then it can come down, spiral dive, right? So fighter jets will have greater tendency. It becomes much easier if the aspect ratio is low. And for many unmanned air vehicles which we use for good maneuvering, we have low aspect ratios for them. Effects on performance. If aspect ratio is high, it will have lower induced drag, higher lift L by D ratios. For example, Boeing 787 will be having aspect ratio around 27 to 30, and aspect ratio L by D ratio will be between 16 to 18. So if aspect ratio is high, it will have longer wings and it will have more bending moments, and the structure becomes heavier. In the case when aspect ratio is low, it will have higher induced drag, it will have better roll rates such that it can go for sudden pull up and sudden pull down maneuvers, it can go for spiral dive in and spiral pull up, and it is easier to manufacture, and it will be compact and rugged. Trades off: higher aspect ratio is efficient for cruise and it will be less maneuverable. Lower aspect ratio will be agile in nature, it will have higher drag, suitable for combat drones or agile UAVs. The moment of inertia about X axis increases with aspect ratio and slower roll response. The shape of a wing in plan form has a significant effect on aerodynamic efficiency, structural weight, manufacturing cost, and flight characteristics. One of the key planform parameters is taper ratio. Taper ratio is defined as the ratio of tip chord to the root chord. In equations, we can write lambda equals to Ct by Cr. Ct is tip chord and Cr is root chord. Three major planform geometries relating to taper ratio are rectangular, trapezoidal, and delta shape. The wing taper will change the wing lift distribution, and elliptical one is desired. The wing taper will increase the cost of the wing manufacture since the wing ribs will have different shapes. If we see suppose this is your root chord and this is your tip chord. So from leading edge to trailing edge, and on this span from the root chord to tip chord, there are different shapes, different cross-sectional area at each segment. So therefore, the ribs which will be installed here will be of different sizes, and this becomes a little bit challenging for the manufacturers. The taper will reduce wing weight since the CG of each wing section left and right will move toward fuselage center line. This is the fuselage center line, which divides the fuselage into two equal halves on the left and right. The wing taper decreases the wing mass moment of inertia about x-axis. Rectangular wing aerodynamic characteristics. Aerodynamic efficiency: generally it is inefficient compared to tapered or elliptical wings. Downwash effects larger at the tip than the root, which leads to reduced effective angle of attack at the tip. The tip stalls later than the root and advantageous for retaining roll control during stall. When we compare this wing, this is the rectangular wing and this is tapered wing, and then we have elliptical wings. These are the three things. In this, we have compared the aerodynamic characteristics of rectangular wing with respect to tapered and elliptical, and also we have tapered wing of this configuration. It will be straight at the trailing edge and it will be tapered at the leading edge. span-wise lift distribution. For rectangular wings, far from elliptical leads to higher induced drag. This induced drag is due to lift, which is inevitable as there is a lift generation. Elliptical lift distribution is ideal, and the purpose of tapering is to ensure that lift distribution is closer to elliptical, which reduces induced drag. For example, rectangular planform wing is having taper ratio of 1. It becomes easy to manufacture. It will have low cost and lower efficiency. Trapezoidal planform wing will have a taper ratio between 0.2 to 0.8, and which is most common in general aviation and unmanned air vehicles. Delta wing, theoretically, it is having 0 taper ratio. It will have high speed and supersonic applications. Delta wings mostly we will be using for fighter jets, and this looks like most of the fighter aircraft will have this delta wing configuration. For example, Rafale, Tejas, Sukhoi. Right? In some cases, it will have twin engines, and in most of the cases, it is single engine. Even Eurofighter Typhoon, F-16, F-14, these all comes under the category of delta wing, which are theoretically the taper ratio is said to be 0, and the best part is they are high in speed, and it is having very good applications of higher speeds, and also the aspect ratio is lower, which leads these kind of wing structures ensuring that aircraft can go for random pull-ups, pull-downs, and vertical climb, vertical dive, spiral pitch up, spiral pitch down. These all categories is attained using delta wing configuration. Wing taper effects. Induced drag. For rectangular wing, it is high, and for tapered wing, it is lower. Induced drag is one of the parameter, one of the drag which is formed due to lift, and we also say that induced drag is inevitable as it is formed due to lift generation. The more lift, the more induced drag is formed. Stall behavior. For rectangular wings, tip stalls later, and for tapered wing, tip may stall first. Stall in the sense is, as I said in the previous slide, it is the point at which the lift tends to dip. This is alpha stall, where the lift starts decreasing after attaining a maximum lift point, and from there it starts losing some lift. Manufacturing cost. For rectangular wing, it is low. For tapered wing, it is high due to the redundancy of the structure. Mass moment of inertia. For rectangular wing, it is high. For tapered wing, it is low. Lateral control. For rectangular wing is moderate, and for tapered wing is improved. Wing weight. For rectangular wing is higher, and tapered wing it is lower. So these are some parameters based on which we will be considering our type of wing. The sweep angle is the angle between the wing leading edge and the aircraft's lateral axis perpendicular to the center line. This is straight wing, and if I slowly curve this, if I turn this, this is the sweep angle, delta L. Sweep angle at the leading edge. Basically, a wing is being swept for the following 4 design goals. First one, improving the wing aerodynamic features like lift, drag, pitching moment at transonic, supersonic and hypersonic speeds by delaying the compressibility effects. adjusting the aircraft CG, improving static lateral stability, impacting longitudinal and directional stability. Types and design strategies. A single sweep angle may not meet all flight conditions, but it will use variable sweep wings to adapt to changing flight regimes. It will have a segmented sweep and it will have a different sweep angles for inboard and outboard sections. Design trade-offs. High sweep suitable for high speed cruise with poor low speed handling, and moderate speed will balance between speed and control. Twist angle. Twist refers to the change in wing incidence along the span. Geometric twist, which is change in incidence angle from root to tip. Typically, it will be negative. And aerodynamic twist, it's change in aerofoil section from root to tip. If the wing tip is at a lower incidence than the wing root, the wing is said to have negative twist or simple twist or washout. Purpose of twist is to prevent tip stall, which ensures root stalls before tip, aiding in controllability, and elliptically lift distribution, which modifies the lift to approximate ideal span-wise distribution. The angle between wing's chord line plane and the aircraft's XY plane is positive dihedral, where wing tips are above the XY plane. Suppose if it is like this, right? So this angle, this is positive dihedral, and this is negative dihedral. This is positive. Negative dihedral is also called as anhedral, which is used in some high speed or fighter aircraft to reduce overstability. The purpose of using this dihedral angle is to enhance lateral static stability, which restores rolling moment when disturbed. The design range for this anhedral and dihedral angles are between -15 degrees to +10 degrees, and it must ensure proper balance between stability and controllability. There are two primary objectives of high lifting devices. First one, maximizing the payload weight and minimizing the stall speed. The primary applications of high lifting devices are during takeoff and landing operations, during which the aircraft speed is slightly greater than stall speed. Since the airspeed is very low compared with cruising speed, the wing must produce more lift coefficient. At the airfoil level, a high lifting device deflection tends to cause the following changes in the airfoil features. First one, lift coefficient is increased, maximum lift coefficient is increased, and zero lift angle of attack is changed. Stall angle is changed, pitching moment coefficient is changed, drag coefficient is increased, lift curve slope is increased. In designing the high lifting device for a wing, the following parameters must be determined: the location of the high lifting device along the span, the type of high lifting device, the high lifting device chord, high lifting device span, high lifting device maximum deflection. And the two main groups of high lifting devices are leading edge high lifting devices and trailing edge high lifting devices. At leading edge, we have the devices which will support to ensure that flow is delayed, flow separation is delayed, and at the trailing edge lift devices we have a flap. 6 basic types of leading edge high lifting devices which are available on practical aircrafts are plain flaps, split flaps, single slotted flap, double slotted flap, triple slotted flap, and Fowler flap. The common types, when we use plain flap, it will have simple hinged flap, the making cost is low and performance is moderate. When we use split flap, it is a lower surface deflection with a moderate cost and higher drag. It will have higher drag here. Single slotted flap, the gap for airflow to re-energize flow, and the making cost is medium and the performance is good. Double slotted flap, it has two element system, the making cost is high and performance is very good. Triple slotted flap, it has three element system and it has very high cost, the performance is excellent. We have Fowler flap, which extends rearward and downward, the making cost is high and performance is high lift. The summary over high lifting device. For sweep angle, the compressibility, stability and CG is adjusted, and it will have fixed or variable segmented range, and it affects on planform and stability of the aircraft. Twist angle improves the stall behavior, and the typical range is between -1 to -4 degrees. Dihedral angle influences rolling response between -15 degrees to 10 degrees. It will just bank. Suppose this is aircraft. This aircraft will bank like this up to -15 and +10 degrees. High lifting devices boost takeoff and landing performance. Conclusion of the lecture. Wing geometry, shape, sweep, twist, dihedral critically influences aircraft performance and stability. Rectangular wings are simple but inefficient. Taper improves lift distribution. Sweep aids high speed flight but affects control at low speeds. Twist and dihedral enhance lift distribution and lateral stability. High lifting devices boost lift during takeoff, landing, and design depends on cost and performance trade-offs. Effective wing design balances aerodynamic, stability, and manufacturability. These are the references covered for this lectures. Thank you.